Welcome back, everyone, and this is our final lesson on graphing polar functions. And what we're going to do today is take a look at the effect of vertically stretching the function and vertically shifting the function. So we're going to start out by taking a look at graphs of y equals 3 plus 3 cosine x and y equals 2 plus 2 sine x, and then use those to make graphs of 3 plus 3 cosine theta. This should be a theta down here, and 2 plus 2 sine theta should also be a theta. So as we did before, we'll start by looking at critical values of those functions in the Cartesian coordinate system. So let's start with y equals 3 plus 3 cosine theta. The 3 out in front has the effect of shifting the graph up 3, and the 3 coefficient has the effect of the cosine function has the effect of stretching it vertically by a factor of 3. So at x equals 0, the cosine 3 plus 3 cosine x is actually equal to 6. At 90 degrees, 3 plus 3 cosine x is going to be equal to 3. At 180 degrees, it's going to be equal to 0. At 270 degrees, it's going to be equal to 3 again. And then when we get back to 360, it's going to be equal to 6. So we are going to plot those critical values, and then, like we have in the past, take a look at what happens in between those critical values. So let's start by graphing the point at theta is equal to 0. We're going to consider our scale to go from 0 to 6, because if we look at our graph up at the top, the maximum value is 6 and the minimum value is 0. So when we're out here on the perimeter of our polar graph, we'll consider that 6 units away from the pole. So we have a point right there at theta equals 0, r equals 6. At theta equal 90, we are going to be at 3. And at theta equal 180, we're going to be at 0. At theta equal 270, we are going to be equal to 3. And at theta equal 360, we're going to be back at 0. So now we've got those critical values plotted. Let's see what happens in between those. Between 0 and 90 degrees, our function is decreasing. So our r values are getting closer and closer and closer to 3. And then between 90 and 180 degrees, still decreasing, our r values are getting closer and closer and closer to 0. Between 180 degrees and 270 degrees, r is at its minimum 0, increasing back up to 3. And from 270 degrees on up to 360 degrees, r is increasing from 3 back up to 6. And isn't that wonderful? It looks like a heart, aka a cardioid. Now we're going to take a look at the graph of r equal 2 plus 2 sine theta. And again, we have a vertical stretch of 2 and we have a shift of 2. So at 0 degrees, the sine function is 0, so r would be equal to 2. That's our first critical value there. At 90 degrees, the sine is equal to 1, so we'd be at our maximum value of 4. At 180 degrees, we would be back at 2. At 270 degrees, we'd be at our minimum of 0, and at 360 degrees, we would be back at our value of 2. So we're going to plot those critical points and then see what happens in between those. So 0 degrees, 2 units, remembering that our scale is from 0 to 6, so 2 units away from the pole. At 90 degrees, 4 units away from the pole. So we're about right there. At 180 degrees, again, 2 units away from the pole, so about right there. And at 270 degrees, we are 0 units away from the pole, so we're actually at the pole. And finally, back to 2 units away from the pole. And so what's happening in between? Between 0 and 90 degrees, R is increasing from 2 to 4. So between 0 and 90 degrees, R is increasing from 2 to 4. Between 90 and 180 degrees, R is decreasing from 4 to 2. Between 180 and 270 degrees, R is decreasing from 2 to 0, and from 270 to 360 degrees, R is increasing from 0 back to 2. And again, we have a cardioid, and it happens to be lying on the positive y-axis. So how do these coefficients, the constant coefficient and the coefficient in front of the sine and cosine function, affect those graphs? So what we would like you to do is experiment with your calculator, your graphing calculator in polar mode, and graph these functions right here and see how they affect the graphs. And when you're graphing those functions, I'd like you to think about these questions down below here and how you would answer them. You're likely going to need several minutes to graph these functions on your calculator and answer these questions. So go ahead and pause the video at this point, and in a moment we will reveal the answers. So here are the answers to those questions, and hopefully what you've noticed that when you graph these functions where the coefficients a and b are equal, you always get the heart shape, or called a cardioid. If you are using the graph of a plus b cosine theta, it has x-axis symmetry. If you're using the graph of r equal a plus b sine theta, it has y-axis symmetry. And there are some other things that you can tell about them as well. To find the intercepts of these cardioids along the axis of symmetry, if you take the difference in the absolute values of the coefficient, you will find that you get 0. So you're always going to have an intercept of 0 on that axis. If you take the sum of those absolute values, it will also give you the other intercept on that axis. On the non-symmetric axis of the cardioid, it will have intercepts that are equal to the absolute value of a, which is the constant coefficient in these functions. The graph of these functions will lie mainly on the positive x-axis if the coefficient of the sine or cosine is positive, and will lie mainly on the negative portion of the axis if the coefficient of the sine or the cosine is negative. For the last polar functions that we're going to graph, we're going to take a look at some examples that look very similar to the cardioids, except the absolute values of the coefficients, the constant coefficient and the coefficient in front of the sine or the cosine function, are not equal to each other. So let's start with our y equal 2 plus 1 cosine x and use that to help us graph r equal 2 plus 1 cosine of theta. Both of these angles should be theta down here. So just like we always have, we're going to plot critical values. At 0 degrees, 2 plus 1 cosine theta is equal to 3. At 90 degrees, 2 plus 1 cosine theta is equal to 2. At 180 degrees, it's equal to 1. At 270 degrees, it's equal to 2. And at 360 degrees, it's equal to 3. Since we are going to be using our polar graph to graph both functions, and I see that the other function, 3 plus 2 sine x, has a maximum of 5, we're going to treat the perimeter of the polar coordinate system as 5 units away from the pole. So let's start by graphing the critical values of 2 plus 1 cosine theta. At 0 degrees, we have a value of 3, so that we will put right there. At 90 degrees, we have a value of 2, so we will put that right there. At 180 degrees, we have a value of 1. And at 270 degrees, we have a value of 2. And at 360 degrees, we're back at 1. Between 0 and 90 degrees, R is decreasing, so we're getting closer to the pole. Between 90 and 180 degrees, R continues to decrease, so we're getting closer to the pole. Between 180 and 270 degrees, R is increasing, so we're getting further away from the pole. And from 270 to 360 degrees, R is increasing, so we're getting further away from the pole. And what you see here is you see something that looks like a cardioid, except it does not have a point at the pole. The last polar function that we're going to graph is r equal 3 plus 2 sine theta. And just like we always have, we're going to start out with the Cartesian version of that, locate critical values, and then use those to help us graph our polar version. So at theta equal to 0 degrees, r equal 3 plus 2 sine theta is going to be equal to 3. At 90 degrees, it's going to be equal to 5. At 180 degrees, it's going to be equal to 3. At 270 degrees, it's going to be equal to 1. And at 360 degrees, we will be back at 3. So, translating that down to our polar coordinate system below, remembering that the perimeter of that is 5 units from the pole. At 0 degrees, r is equal to 3, which is going to put us right there on top of that point from earlier. At 90 degrees, r is equal to 5, so that's going to put us out here. At 180 degrees, r is equal to 3, so that's going to be about right there. At 270 degrees, we're going to be at 1, so that is going to be right here. And when we get back to 360 degrees, we're going to be back at 3. And as you can see from the graph up above, between 0 and 90 degrees, R is increasing, so we're getting further away from the pole. Between 90 and 180 degrees, R is decreasing, so we're getting closer to the pole. Between 180 and 270 degrees, R is decreasing again. And between 270 and 360, R is increasing again. And again, you will see a graph that looks similar to the cardioids, except they don't have points on the poles. These are called limacons. We would like you to experiment with various values of the constant coefficient and the coefficient in front of the sine and cosine function using these functions below, and then use those to answer these questions. So at this point, you should pause the video, experiment with your calculator, and we will post solutions on this video shortly. These polar graphs r equal a plus b cosine theta and r equal a plus b sine theta are called limacons when the absolute values of a and b are not equal. If it has a cosine function in it, it has x-axis symmetry. If it has a sine function in it, it has y-axis symmetry. It will have an inner loop if the constant coefficient's absolute value is less than the coefficient of the sine or the cosine function. You can find the intercepts along the axis of symmetry of limacons by taking the difference in the absolute values of the coefficients and the sums of the absolute values of the coefficients. The intercepts along the non-symmetric axis are equal to the absolute value of the constant coefficient. And as before, if the coefficient of the trig function is positive, it will lie on the positive axis. If it is negative, it will lie on the negative axis.